Okay, so the first problem we have here says we have a fly caught in a spider's web, creates a wave pulse that alerts the spider to the presence. So we have it's kind of here at position A, and supposedly the spider is here in the middle of the web at what's labeled as position C. Um, we're given kind of some information here about the size of the web, and we're given a bit of information here about kind of the physical specifications of the web. So we have a mass density and a tension. And the whole point of the question, we're told here, is to calculate the time it takes the pulse to reach the spider traveling along path 1 and path 2. And at the end of this, we all want to figure out a time difference. So in kind of the dashed line here that passes through points A, D, E, and then to the center of C, that takes up time, and apparently there's a wave that passes through that path. And then through this dotted line on the left that passes through A, B, and C, there's a second wave. And the kind of the interesting note that places this with some, I don't know, real world relevance says that this is actually useful because it helps spiders actually do this, and it helps them determine where exactly on the web something like a fly might have landed. So there's a few ways we can get started. Really what we're doing is we want to calculate a time for path 1 and a time for path 2, and by the end of this we want to calculate delta t, which is just obviously the difference, t1, or sorry, t2 subtracted t1. We can pretty easily, from the information that's given here, we're given the distance between A and B, B and C, and then B and E. And we can kind of figure out that this is a regular pentagon, which means all 5 of the external sides are the same length. All the angles in here are all the same. So from that, we can figure out if we have A, B, C, and D, E, we can figure out basically all the other side lengths. So we can figure out what the distance the wave travels in each case. And then if we can figure out the velocity, we can calculate the time. So that's just kind of regular kinematics from very beginning of last semester. So what I'm getting at is if we want to figure out the time, and we can deduce what the distance is, if we have a way to find the velocity, we can find that time. So perhaps if we need to figure out what this velocity is, that's kind of the only thing, the unit you guys are working on is waves. That's really the only wave related thing. The rest of it is just geometry and some basic kind of kinematics. So let's start off finding out what the velocity is. So the relevant quantities of interest are this linear mass density and the tension in the strands make up the web. So what I think you guys should have seen already is that if that string carries a wave, the speed of the wave along that string is related to the tension and the linear mass density. I think there's a typo when this was arranged. This should not be rho. I think the variable you guys is mu. So tension is T, the mass density is mu. And this defines the speed of the sort of string, cable, wire, whatever you want under tension. So we can calculate this really quickly and then just put it aside while we work with the rest of the problem. So the tension is 1.66 times 10 to the minus 3 newtons. And the mass density is 9.18 times 10 to the minus 6 grams meter. Note that grams is not an SI unit. When you're dividing this into something like newtons, you want to perhaps change this to kilograms. I'm going to spare you guys the details and trust that you can do it on your own. So if you put this into your calculator, do all the unit conversions correctly, you'll get about 425 meters per second. So that velocity we're going to eventually want to plug into here, but let's put this aside for the moment. We figure out what the distances are. So let's say that the distance, we'll call this d subscript 1, and I guess that makes sense because this is path 1 right here. That equals the distance from A to B plus the distance from B to C. And we could take the velocity now and we could figure out what these numbers are. We have A to B and we have B to C in these details up here, and we could plug this in and we can get a number. But I think that actually makes the computation a little bit more challenging. So I'm going to solve this through the rest of the way in variables, and then we'll see that perhaps it's a little bit simpler. So we have, this is good enough right now for the distance along the first path. We need to figure out what the distance along the second path is. We have dA to D plus the distance from D to E plus the distance from E to C. Now, at this point, if we quickly glance at what parameters we were given in the preamble for the problem, we have what I've been calling DAB. We have DBC, and we have D to E. We don't have A to D. We don't have E to C. But we can look at the fact that this is like it's a regular pentagon. There's a lot of symmetry going on here. So DE to C is pretty obviously the same as DB to C, and we have DB to C. So we'll take this one, swap that out for DBC, and DA to D might require a little bit more thought, but it's not too complicated. Notice that every single one of these 5 sides is the same. So the distance from B to D is exactly the same as the distance from D to E. So I think it should be somewhat clear that DAD is just the distance from D to E minus the distance from A to B. So it's just a side length. It's the full side length minus this kind of this sliver right here. So that will leave this bit here. So we can rewrite D2. That's equal to D from D to E minus the distance from A to B. That's what we replaced this with. Plus the distance from D to E minus the distance from B to C. So altogether, we have 2 times the distance D to E minus DAB minus DBC. Both distances, we have a velocity, we want to compute a time, we're pretty much all set. So the time difference, like I said at the start, is the distance between the times, the travel time along both paths. T2 is just going to be equal to D2 divided by the velocity. T1 is just going to be equal to D1 divided by the velocity. So D2, we're just going to rewrite what we had above. And what we will find is that this V is the same in both cases. Notice that I did a subscript 2 and a subscript 1. That's because the waves are traveling, the one that goes through path 1, the one that goes through 2, they're traveling through the same type of material, whatever this spider web is made of. So if the material is the same, the wave speed will be the same. So what that means is these V's are the same, and I'm going to write these distances over kind of like a common denominator. I'm just going to kind of start simplifying all this stuff. This is all over V, like I just hinted at. Notice that we have a dBc in both terms. So this simplifies down to 2 times the distance from D to E minus 2 times the distance from A to B. So we can just sub in the values that we have. The distance from D to E is 11.8 centimeters. AB is just 3 centimeters. And that velocity that we found, or the speed that we found, was 425 meters per second. And what we find, put that into your calculator, make sure you do something with centimeters so that they work nicely with this meter here, so you have to do a unit conversion. But you should find something just a little bit above 400 microseconds, or 400 times 10 to the minus seconds. Something like that. So in case you guys are trying to make connections, or if this is in any way a bit fuzzy or a bit confusing, like I said, this is kind of connecting to the stuff you would have seen in lecture about waves going along a string. In particular, this is related to the speed of the wave. On a string which is under tension. So that's kind of really the whole wave topic here. The rest of this was just geometry and recalling the relationship between distance and velocity and time from the very beginning of last year. So this is really kind of the topic for this question. Problem 2 here is a bit mathy, so if that bothers somebody, I apologize in advance, but I think it's pretty simple and hopefully easy to understand. So we're supposed to show that the following equations represent the form of a traveling wave, and we're going to want to figure out from that what is the phase speed. So the kind of the mathematical form of a traveling wave is that you can write the disturbance, imagine that there's a disturbance in the y direction, as some function of the position minus the speed times time. So it's a function of x, the position, and it's a function of time. And if you can represent something kind of with this form sandwiched into some bigger function, then you know you have a wave. It's about as detailed as it gets. And the number that's attached to this time is the velocity. And really the minus sign here is just to help us with direction. So if you see something that is a function of x minus 7t, if this is minus, it's moving to the right. And the velocity, if x is years and t is in seconds, it would be 7 meters per second. If you had something else, a different function, and it was x plus 4t, something like that, the wave would be moving to the left, and it'd be a velocity of 4 meters per second. Again, assuming that x and t are in meters and seconds respectively. So the whole point of this question, we're given 3 equations. We want to kind of work with the functions and simplify them and see if we can manipulate this so that we can arrive at something that has x minus vt sandwiched in there somewhere. So a is a quadratic. We have kind of a term for x squared, we have a term for t squared, and we have a kind of a cross term that has both x and t. So it kind of naturally lends itself that we could write a as kind of something x. There might be a plus or a minus. There'll be a t here, and imagine that's all squared, and we just need to figure out what the term is here that's attached to the t. It's slightly more complicated than that. Hopefully quadratics are no big deal for you guys. But if you factor this, you'll get 2x minus 7t. If that's a little bit fuzzy, just work it backwards, just square the whole thing and make sure that you get this. And what we want to get is we want to get a function that has x minus vt. We don't want 2x, we just want x. So what I'm going to do is I'm going to factor out the 2. That'll end up being 4 because we're going to pull it through the square. We'll be left with x minus 7 over 2t. So in this case, our velocity, again, we're going to assume x meters and t is in seconds, is, and we've kind of arrived at this form here where we have x minus vt, with v being 7 over 2. So pretty straightforward stuff, pretty simple, I think. The second one here, we have a fraction that has a couple exponentials in it. So this kind of we just want to go through the same process. The only real key is making sure we know what to do um, with exponentials. So in this case, when you have in the numerator here, we have exponential x. That's just some function, or sorry, the exponential function with x shoved into it. That gets raised to the power of 4. So that gets raised to the power of 4. We can rewrite that as exponential of 4x. So the nature of the exponential is just that we can bring the 4 in. Hopefully you guys are somewhat familiar with exponentials. It's not super duper important, but hopefully you guys can manage this. And then on the bottom we have 8t. This is like having the exponential of 8t in the denominator of this fraction is the same thing as writing exponential of 4x times exponential of minus 8t. And then if these two are multiplied by each other, we can simply write exponential of 4x minus 8t. At this point, we're pretty much set. We just need to do one factor before we can have kind of x by itself. So if we factor out the 4, we're left with x minus 2t. There's kind of the form that we're looking for. So this is just a velocity of 2 meters per second, and this is indeed a function that could drive a wave. And the last one's just a really abstract one. There's no numbers, it's just a functional form. We have a sine times kx minus t as the argument of the sine. So what we can do here is all inside the sine. It's really hard to factor stuff out of sines. It's not straightforward, but what we can just do inside the sine is we can divide everything by k. And I'm running out of space, but we can get x minus omega over k times t. And this is totally fine. We have this kind of, this looks like x minus vt, except it's x minus omega over k. So clearly what this means is that the velocity in this case, this is indeed a wave, and the velocity is just omega over k. And the only reason that we included this is because this is actually going to come back, and you'll see this in later lectures. It's a very familiar form, but just showing that you can do the same process with without numbers, just with entire variables. So this, if you guys have to look at the kappa, and if you guys have paid attention in lecture, this is kind of just the mathematics or the mathematical representation of a wave or a wave pulse. As long as it satisfies this kind of form that's written here, then you guys can, with high confidence, know that that's into a function of a wave. Okay, so I think the first two questions are pretty straightforward and pretty move through. The last two we're going to do are on history and snapshot graphs, which I think some students have some trouble with. So what we're going to do is we're going to go through this problem, and it's really almost painfully down into the various steps. But we'll go very step by step, and hopefully we'll give a good template for solving these and kind of doing these transformations from one graph to the other. So for problem 3, we're given a snapshot graph right off the start. So snapshot, in case the terminology is not something that we're comfortable with yet. A snapshot is like, imagine you have something unfolding in front of you. You can see what's happening in Y, you can see what's happening in X, and you just take a picture of it, you freeze it. So at a particular point in time, you just look in front of you, take a picture. So you have Y versus X. If you have position on both your axes, you know automatically you have a snapshot graph. Oftentimes you will see a snapshot graph labeled with what time the snapshot has been taken at. So in this case, we're told that it's at t equals 4 seconds. You can imagine at 5 seconds a different snapshot, at 6 seconds, etc. The pulse moves with a phase speed of 2 meters per second to the right. So we can label that as well if we want to have it handy. So part A, which is the step of our process, is asking us to identify 4 points that define the shape of the wave pulse within the graph. So this is just a single pulse. It's not a repeating wave or a periodic wave. It's just a single pulse that's traveling. It's going to the right. And if we're going to transform this to a history graph eventually, we want to know kind of what points are useful to transform. We don't want to transform 100 different points. You could imagine that, notice at 12, y is equal to 0, 13, y is equal to 0, 14, y is equal to 0. These are not useful points to transform because there's kind of nothing happening there. So we kind of need to pick a minimum number of points and go from there. So we have, usually it's the corners of the pulse are the useful and interesting things. And it's probably really hard to see, but there's a slope change here at x equals 8. So this bit is a bit steeper. This is a bit shallower. So that's why I'm picking out this point here at x equals 8. If you don't look carefully, it might just look like I'm picking a random point in the middle of what is just a triangle, but it's not actually a triangle. So we have 4 points. Part B wants us to label them. And then we just want to take the coordinates off this graph and write them into the table below. So I'm just going to work left to right. So we have P1, P2, P3, and our 4th point is P4. And then we want to label these, and these are points in position and time, right? This is the snapshot at 4 seconds. It's not the snapshot at 5 seconds or 6 seconds. But because this is a snapshot and all these points are taken at t equals 4 seconds, we can immediately just write in 4 seconds. And then we can just go through and get the positions for all of these. So P1 is at x equals 2, y equals 0. P2 is at, it's actually at x equals 7. If we take a close look and I draw my line straight and all that kind of stuff, it's at x equals 7. Y equals 2. P3 is at x equals 8, y equals 1. And the last point, P4, is at n and 0. So if you guys doubted me that there's a slope change here, I think it should be a little bit more obvious. Now that we've given values to these points, you can count the slopes between them if you want it for yourself. But we have the 3 coordinates for each point. And now part C says determine when each of P1 through P4 pass through point x equals 6. And we're going to ask to kind of, once we figure out when this happens, we're going to fill out the coordinates in a kind of a new table. So these are going to be our transformed points. And if we head, we're going to use these to put together a history graph. So the key things to identify here, this might not be how you were asked to solve a problem. I think in a kappa, you might just be said, make the history graph, right? So this is very drawn out, and this is why you're being asked when you don't even know what you're doing. But you can kind of piece together that if you're being asked for when, you're looking for a time, and you're looking for a time when things happen at x equals 6. So from that, you can say, I'm probably going to be asked to make, a history graph, because history graphs involve time, and I'm probably going to be looking for a history graph at x equals 6. So how exactly do we calculate when these points are passing through x equals 6? We know exactly where they are at t equals 4. So we have the position, we have the time, we have it really well sought out at one instance, and we know what's going on at another instance. So really what we're trying to do is realize that there's going to be a change in position due to the fact that the wave is moving, hence the velocity. And we're looking at different time instances. So really all this is saying, if you put it into words, is that as time unfolds, the wave moves. That's really all that means. we can break down kind of this delta x and this delta t into explicit terms. So there's a change in x and a change in t. And let's pretend that the initial conditions, the xi and the ti, or not pretend, like this is just the xi and the ti, we will take them from this table. I guess I can't draw a cross line, it's page breaks. We will consider whatever's going on in our snapshot graph, that will be the initial points here. And the final will be what happens when the point of interest, be it P1, be it P2, that kind of thing, when it passes through x equals 6. So what that means is that xf is always going to be, this might sound weird. I think if I start just kind of moving through and showing a few calculations of what I mean, I think it will make sense in case it's not making sense to anybody else. So let's start with P1. Do I want to start with P1? Maybe just before I start with P1. We want to be calculating a time. We want to be calculating this time when the point is passing through x equals 6. So let's just a quick bit of algebra to get at TF so we don't have to do it for every single point. We'll just do it once now and arrive at an equation that we can reuse 4 times. So I think we'll find that TF is equal to xf minus xi divided by v plus ti. So I just divided both sides by v and then added ti. So this is kind of the master equation that we'll use in this case. So let's do this for P1. Let's actually kind of do a calculation and hopefully have things start making sense. So we want to figure out what is the time and P1. If you guys have forgotten what P1 is, it's this one down here. Let's find out when this passes through x equals 6. That's right here. So this whole wave is moving to the right. So we probably predict, we just look at this, it's going to pass through x equals 6 at some later time. So we said that the point we're trying to end up at is x equals 6. That's what we denoted here. xf is always going to be 6. It started out at x equals 2. As we said, all of our initial conditions are going to be on the previous page. The velocity, I don't remember what the velocity is. It's 2 meters per second. And the ti, again, we said that comes from the previous page. It's always going to be 4 seconds. So 6 minus 2 is 4, divided by 2 is 2, plus 4 seconds is 6 seconds. So let's see if this actually makes sense. Supposedly at 6 seconds, the point P1 is going to pass through x equals 6. So we're moving at 2 meters per second. In a second, it moves 2 meters. So at 1 second later, it'll be here. Another second later, 2 seconds later, it'll be at x equals 6. So that's exactly what we just calculated. It's kind of just a graphical confirmation of that. Next, let's move on to P2. And before we scroll down, let's kind of choose, kind of like, let's try and predict what we'll find really roughly. So this is at x equals 7, remember, I've labeled 2. So at 4 seconds, this crest here at the very top is at x equals 7. That means if this is moving to the right, it's already been at x equals 6. So it was at x equals 6 some time ago. In other words, we should calculate a time that is less than 4. So let's see what we get. So we're trying to solve for the time when P2 is going through x equals 6. So that means x equals 6 is our final position. Our initial position we just said was 7 meters. Divide that by velocity, and our initial time from the previous page was 4. So we get minus 0.5 seconds plus 4 seconds, which equals 3.5 seconds, which is smaller than 4 seconds. So kind of what we predicted to happen did happen. Note that, so we can kind of avoid jumping back and forth another time. P3 and P4 are also past x equals 6. So that means because the wave is moving to the right, they've already been through x equals 6. So again, we'll calculate the times for our history graph, but we expect them to be smaller than x equals 4. X equals 4 is just when we had this particular snapshot. So 0.3, we're trying to find out when it ends up at x equals 6. In our snapshot above, let's glance at our table. It was at x equals 8. I seem to have lost my pen temporarily, so let's try and fix that. Seems like everyone is very silent in the chat, which I'll take as a good sign that everything is making sense, and this is either very simple concepts or my explanations are really incredible. But yeah, don't be shy if anything is, if I make a mistake, if something's not clear. If it's not clear to you, it's probably not clear to somebody else. Or just arbitrarily post in the chat to say hi. So thank you. I appreciate the confidence. Yeah, so proceeding onward with 0.3. Basically what this first term means, we'll calculate out that this fraction is minus 1 second. It means that 0.3 was at 6 meters 1 second prior to when we had our snapshot at 4 seconds. So putting that from clumsy English into just kind of a simple number, it was at 3 seconds. And I'm running out of space, so let's just do P4. When does that end up at 6 meters? It started out in our snapshot above at 10 meters. Velocity is 2 meters per second, and our snapshot was taken at 4 seconds. So 6 minus 10 is minus 4 divided by 2 is minus 2. Minus 2 plus 4 seconds is 2 seconds. And we can take all these and complete our table of transformed points. So once we have these transformed points, we're just going to basically put them onto the graph that I already showed you guys below. So all these end up at x equals 6, because that's where we've calculated the history of. So that's pretty straightforward to calculate. The vertical positions, like where the peak is in this graph, where P2 is, that doesn't change, right? We're just moving side to side. It's moving to the right, moving to the left, depending on which direction you're letting time roll. So all these are the same. So we can just copy the y column from above. And now the times are the interesting detail we calculated. So P1 was at 6 seconds that we calculated, 3.5 for P2, 3 for P3, and 2 for P4. So I'm just going to double check with my notes, make sure that, yeah, that's what I have here as well. So we can just put these now from the table onto our graph and maybe just chat really quickly about what, if it makes sense, if it looks right, what's the expected behavior, that kind of thing. So I'm going to go left to right. Actually, what we're doing, if you notice the times, we're going from P4 up to P1. Because kind of the order that we arranged them in, P1 to P4, the times have now kind of, the order's reversed. Okay, so at t equals 3, we should have, try to do this decently. There's P3. At 3.5. We have the crest, and then all the way down at 6, I think, yeah. We have this. So we have our 4 points, and we know that outside of these 4 points, the wave is just kind of, there's no waveform, it's just at 0. So just really quickly jot in these, what is now the leading edge on our history graph, and I'll try really hard to draw this so the slope change is obvious. That was not very good. Maybe I'll fudge where this is a little bit. Yeah, so I'm just really trying to nail where this is at 3.5 so that we can have an obvious, yeah, there we go, looks a bit better. Obviously, if you guys were doing this on a test or something like that that was written in person, you were, and it would look fabulous. But yeah, so this is our history graph. It's always good to denote on the graph that it's at x equals 6. The velocity, it's a little bit weird on this. What velocity? You can't visualize velocity as well, but it's 2 meters per second. Good to have that noted here. And just so that we can refer back to our table, I'm going to note that these are in reverse order in case we forgot. So the key thing to note here is that when you have, I think this is a rule, so I think you can kind of take what I say and verbatim just apply it to, if you have the velocities to the right, then if your snapshot looks something like wave like that, then your history graph is going to be flipped. This is pretty, I think this is pretty foolproof, so you can quote me on that. Obviously, you want to do the calculations and verify, but just if you get to the end of your question and you want kind of what's a quick, simple check, and similarly, if it's if your snapshot looks like this, then the cool thing is that your history graph will also look like this. So ours is right. We had this kind of weird side with the bend. It's on the left in the history graph, and it's on the right in the snapshot graph. Cool. So this looks good, despite the fact that my drawing is very low quality. Part E says there are 5 distinct parts to the motion in our history graph. Determine the speed of the particle during each and label directly on the graph. So the point of this one is to distinguish this question is that the whole wave is moving to the right and the whole wave has velocity, but the way that we treat this, and this is what's kind of highlighted in italics here, is imagine this wave is propagating down a string and there's a particle at x equals 5. There's a particle at x equals 6. We consider that particle to be fixed at x equals 6 in terms of the x direction. It doesn't move left, it moves right. But when the wave passes through it, it kind of moves up or down. If you've ever been at like a hockey game or basketball game and the audience does the wave where everyone raises their hand kind of in a synchronized manner, kind of you stay in your seat, right? You just stand up and you raise your arms. It's the same idea. So there's a vertical displacement even though the wave is moving perpendicular to you. So I saw there's a question. Okay, so John says my audio dropped for a second. Why are the 2 left waves not flipped? It's because I kind of was just giving you guys a bit of a rule for what the relative orientations are. When you have velocity moving to the left and velocity moving to the right, I don't really think I have a great explanation for you other than if you run the numbers and you do enough of these, you actually do the calculations, you'll just find it to be true, I guess. I'm sure there's a clever answer that you could maybe reason through with like the geometry and the relative orientation of the wave features versus the velocity, but the reason I know is I've done enough of them and I find that when it's moving to the left, you preserve the shape, and if it's moving to the right, you flip the shape. It's probably because we have time. We like to put time axes with time increasing to the right, is basically what it is. Yeah, cool. Okay, so we want to figure out what is the speed of the particle at x equals 6, and this is kind of the y speed. So again, I don't know if this concept is, if I'm doing a good job with this one, but as for instance, this particle here at x equals 12, as the wave passes through it, as it starts to ride up this part of the wave, it ends up moving upward. So, yeah. So basically what this means is we want to know what is the change in y in a given amount of time. That's velocity, right? Vy is equal to delta y divided by delta t. Lo and behold, we have a graph of y versus t. So this just boils down to figuring out the slope. And we have the points that help us define our slope. So I think we're set. These ones are really easy. There's 5 that we're told to find, 5 slopes. This is 0 meters per second. This is 0 meters per second. This is 0.2. This is 1.3. So this is a y change of 1, an x change of 1 as well. So I think that's 1 meter per second if I'm not wrong. This is a y change of 1, an x change of a half. So that's 2 meters per second along this slope. And what's this one? This one is, I have these backwards in case anyone should have called me out. 2031. This one's at 3.52. This is 60. So this one ends up being, what is this? We have a change of -2 divided by an x change of 2.5. So that's slope is 0.8. Yeah, good call. So Alex caught my units. I wasn't paying attention. So yeah, all these slopes in centimeters per second. But yeah, got a bit messy, labeled them on there, but I think the point stands, right? Cool. So problem 4 is basically going to be the opposite. We're given a history graph to start out, and we're going to work through the process of generating the snapshot. The process is identical. Clearly the shape of the graph is a little bit different, but the process is identical. So we have 10 minutes left in our kind of allocated time. I'm happy to go over if needed, but I don't think we need to. I'm just going to go a bit faster. So this is a history graph. It's at x equals 4, and we're told that the pulse is moving to the left. So I'm just going to give it a negative sign for the speed at 0.5 meters per second. We have y in centimeters, we have t in seconds. So we weren't told it was a history graph. We can still deduce that it's a history graph. So we're going to go through and label 5 points that kind of help us define the curve. And what I said before, we were going to try and find the minimum number, I think. Minimum was perhaps a bad term. We want to use as many points as we need to nicely define the pulse, and so we can draw it. So previously we kind of needed the corners. In this one, this is a sine curve, or a piece of a sine curve. I want 5, like having these points at 0 and the 2 extreme, max and min. I think that's what we need to solve this. Yeah, so Wallace asked what was the answer to the previous question. The answer was just kind of the slopes at each point. So a little bit messy here, but it's, here, let me, it's basically using the points and figuring out kind of what is the slope along this line. So sorry for getting a bit sloppy. Okay, so we have some points on this pulse. I'm going to label them P1 to P5, going left to right again. Part B says which points collide with the greatest speed upwards and downwards. And just for, like I said, I'm going to try and go a little bit quickly. Notice that the slope here, here, and here is steepest, so it's going to be P1, P3, and P5. I'll leave it to you guys to figure out up versus down. So part C says fill out the coordinates, so we're going to basically repeating what we did last time. History graph of x equals 4. So that means we have a y and we have a t for when they're at x equals 4. So we can just fill in the first column entirely with 4s. So at 2 seconds, 0.1 was at 0. 2.5 seconds, we have 0.2. I guess I can probably fill in the y's pretty easily and just go through and pick off. So I don't know what you guys have talked about in lecture yet, but we can already see that these points are regularly spaced with half-second intervals between them, and the whole span is 2 seconds. This kind of like, just the sign bit here has a period of 2, but if that doesn't make sense, just you'll be covering that in the next lecture, I guess, if it doesn't make sense now or soon. Okay, so we want to transform these points that we have here so that we can end up making a snapshot graph. So we're told to do this at time equals 6 seconds. That means we're going to be making our snapshot graph at t equals 6. So we'll start with the same formula we did last time, that the change in position is equal to the velocity times the change in time. And we can break that up, or expand it, I guess, to look like this. Yeah, P4 should definitely be -1. Thank you for pointing that out. Okay, so this is the equation. I've kind of solved it a little bit differently than last time. Because we want to find out, it says determine the location at time t equals 6. So we're going to get our initial conditions, our ti and our xi. This is x. We're going to get that from the previous page. And our final, well, we want to find out t is equal to seconds, and we're going to want to calculate the position, or the location, as it says right here. So this is how we're going to fill in this equation. And once you kind of have this figured out in your mind, where am I getting my initial quantities from, which of the final quantities is given to me, and which one is left for me to calculate, it just becomes kind of plug and play, right? So we can move forward with that. For P1, we want to solve for a position. Our velocity is minus 0.5 meters per second because it's moving to the left. If at this point we forget that it's moving to the left and we don't bring this negative along, then we will run into the. So I guess just try and keep your wits about you and remember that. So I just erased it, but TF is always going to be 6 seconds. TI we're going to take from the table. 2 seconds. And we're going to add to that xi, which also comes from, xi is always going to be 4. So this difference here is 4 seconds. We want half of that, and we're going to make it negative. So minus 2 meters plus 4 meters. And we just repeat. So this time we're calculating with 0.2. We want to know it's going to end up at, we want to know what it's doing at 6 seconds. TI from our first table is going to be 2.5. And what is this? This difference here is going to be 3.5 seconds. So half of 3.5 seconds is 1.75. That's got a minus attached to it. So I think that's 2.25. Mental math is hard though, so but I think it's 2.25. And yeah, I think we're getting on in time. I think if you guys try it on your own and maybe you can see the pattern already developing, but these points are evenly spaced. Notice that I'm basically losing point, or I'm gaining 0.25 every time. So this is going to be 2.5 meters, 2.75 meters, and I think we end up at x equals 3 by the time we're all said and done. So we had 2 questions there. What's the answer? B in problem 4. Like this entire recording is also going to be uploaded, so I know it's good to have it now, especially when you want the answer. It will also be available in its entirety shortly after we're done here. Okay, so we can fill in these values that we just calculated. So 2, 2.25, 2.5, 2.75, and 3. The values don't change. Remember, the wave is just sliding to the left or sliding to the right. But the fact that if we're looking at this feet in the wave, where is the crest? Well, the height of the crest is always going to be at 1. So basically what we're doing is we can just take the y's and copy them down. And if you go back or think to what we did in the previous question, we had table 1 and we just copied the y's down to table 2. So it's pretty safe to do that every time. And because this is a snapshot graph, the snapshot's being taken at 6 seconds. We can just fill in 6s everywhere. That's our second table. We're basically ready to put together our graph. Yeah, so Shipang just asked, is this going to be recorded? Of course, it will be recorded unless I forget to turn the recordings on, and thankfully I did not do that this time. So we're recording the whole time. I don't know if the questions, the chat shows up in the recording. I don't think it does, but yeah, me talking and the solving, that will all be uploaded. Okay, so let's just copy basically our points from our table onto our graph. So we want to put a point at 2, 0. I think our scale is a little bit, it'll be fine, but it's just a little bit shifted. So we have 2, another 2.5, and another 0 at 3. Something like that. So I just drew all the zeros first because they're easy and they're in a line. We had the crest at y equals 1, x equals 2.25. So 1's up here, 2.25's kind of in the middle, and that leaves the process of elimination, kind of the deepest trough there. So yeah, you can see that all the action was happening between 2 and 3, so the scale is a little bit inconvenient. But we can kind of put together a hand-drawn sine curve that does a pretty good job. And remember, we kept track of what was P1, what was P2, etc. throughout the whole calculation. So these features are kind of labeled left to right in this one. If we're working, we read this with our eyes from left to right, we go through a crest and then we go through a trough. So the shape is the exact same as we had here. The orientation of these various features is the exact same. It's all kind of consistent. And like I said, if the wave is traveling to the left, you kind of preserve the orientation. And if to the right, we flip. So we kind of had another good example to support that. So that is the end of kind of the document I have. I can stick around for a few more minutes. We're 2 minutes over, but I have a bit more time if there's any questions that come up. Like I said, this will all be uploaded. The document should be up already. The video will be up. It takes a bit of processing time, but should be up within a couple hours, I think.